So, hello guys, this is our first problem for chapter 23, and this problem has quite a number of formulas to be used. So, I'll explain that later. So, here's the problem first. Two protons are released from rest when they are 0.750 nanometers apart. For part A, what is the maximum speed they will reach and when does this speed occur? For part B, what is the maximum acceleration they will achieve and when does this acceleration occur? So, there are four formulas that we need to use for this problem. That's quite a lot. I think that's the most we've used for the past videos. And here are all of them. Here, let's highlight that properly over there. So, these are the electric potential energy formulas. This is the conservation of energy formula. This is the Coulomb's law formula if you guys are familiar with that. And Newton's second law, F is equal to ma. So this is our representation of electric potential energy U. And it's similar to our Coulomb's law formula except the difference is simply the distance or the radius under at the denominator rather is not squared, and there's no absolute value for the charges. And yeah, it's pretty self-explanatory really. It's similar to our Coulomb's law formula. Next would be our conservation of energy formula, which again, this is our U, this is our potential energy, similar to our electric potential energy formula, this except these I subscripts and these F subscripts denote initial and final respectively. Here I've noted that K is kinetic energy and U is potential energy. And again, if you guys are familiar with kinetic energy from our previous videos, it's essentially 1/2 mv squared. So, again, this is our Coulomb's law. I don't need to explain that further. And this is our Newton's second law, which has been used previously as well. So, in order for us to solve this properly, we need to list down our given. Technically speaking, we only have one given value. This is 0.750 nanometers. And yeah, that's just that. So I just put it over here as 0.750 nanometers. But you can also change it to meters by simply multiplying it by times 10 raised to 9. And that's essentially converted to meters already. But let's list down all of our given values, even the constants, except for the pretty obvious ones like 9 times 10 raised to 9, the proportionality, K constant. And here's why. It might confuse us later. So, here there are two protons. So, we both know that the two charges are protons. Here, two protons. We know that they will have essentially the same charge, same mass. And as you can see here, they were both released from rest. So, they would have similar values for the VI as well. So in order for us to make it easier for us to substitute later to our formulas, let's write those values over here instead. So as you can see over here, this is our Q1, Q2. As you can see, there's a bit of an error over here. Should be negative 19 coulombs. So this is the charge of a proton, positive 1.67 times 10 raised to negative 19 coulombs. And as stated in our problem, it's released from rest, so that would mean our initial velocity is 0. Then again, our 0.750 nanometers. And now we can identify our unknowns. For part A, they're looking for the maximum speed. So that would mean they're looking for final velocity. And when it occurs, take note that for both parts A and B, they're not asking for a definite time value. They're simply asking for around when will it happen in the course of time. Like, will it take a bit longer? Will it will it happen immediately after the release? Something like that. And for part B, they're looking for maximum acceleration. And yeah, similar to part A, they're also looking for when it occurs. And here I have a short explanation as to how we could simplify our solution for this problem. Since the two charges are both protons, in short, they have the same mass, same charge, and even the same initial velocity since they were both released from rest, we can say that their final velocities would actually be equal. Likewise, their accelerations will also be equal. Therefore, we only need to solve for the final velocity and the acceleration of one proton to solve the following problems. That makes it easier. So now let's get to our solutions. Let's solve for VF first, which we can solve by solving first for our electric potential energy U. So again, let's get our formula over here. U is equal to KQ1Q2 over D over here. And we can simply substitute all of our given. This is the proportionality constant K. Again, these are the charges of the protons. This is the first proton, this is the second proton, so both of them have the same charge. And this one is the distance between them, which was, according to our given, 0.750 times 10 raised to 9 meters, or 0.750 nanometers. And if we plug that into our calculator, solve for it, we can get 3.07 times 10 raised to negative 19 joules. However, we should note that this is the electric potential energy of the two protons. So, in order for us to get the electric potential energy of just one proton, we can simply just half this value, this 3.07 times 10 raised to negative 19 joules. And that would be our EPE for our one proton. That would be important for our next part of the problem, which is the conservation of energy formula in order to solve for our VF. Okay, so here we go. This is our Ki plus Ui is equal to Kf plus Uf. So we should note that maximum speed is obtained once all potential energy is converted to kinetic energy. So we could say that our final potential energy is 0. So as you can see, for our substitution over here, I've put 0 for our UF, which is our final potential energy. So next, this is simply the substitution of the formula for kinetic energy, 1/2 mv squared. Except now we're putting the VF over there since, it's the final velocity. Then next, this is our initial potential energy. And as you can see over here, this is what I was saying earlier about the EPE of one proton. Since again, we're only going to solve for the velocity of one proton to make it easier for us to solve for the entire problem, we're only going to use half of it. Half of the 3.07 times 10 raised to negative 19 in order to solve for our problem. Then, notice how I've highlighted this in red. So, you know how our given is 0 meter per second for the initial velocity, right? Since they're both released from rest. So that would mean this entire thing essentially gets cancelled. So it's going to be equal to 0. So, in short, we would be left with this formula. mv squared f is equal to 3.07 times 10 raised to negative 19 joules. Since they both have the same factor of 1/2, we could just cancel that 1/2 and we'd be left with this equation. mvf squared is equal to 3.07 times 10 raised to negative 19. So we could just divide this value by our mass, then square root everything that on that right hand side as shown over here. And you know the mass of a proton is 1.67 times 10 raised to negative 27. So I'll put that over there. So let's put that over there for clarification. So that's going to be how our formula looks like when we plug it into our calculator. And don't forget the square root, since again in our initial formula our VF is still squared. So by applying the square root, we would basically get the actual VF value, and that would be this 1.36 times 10 raised to 4 meter per second. So it's a final velocity, so it's not likely to happen immediately after release, and it's more likely to happen a long time after the protons are released from rest, since they need to accelerate first in order to obtain more speed, and in order for them to convert their potential energy to kinetic energy. So that means that will take time, and that wouldn't in short, that wouldn't happen immediately after release. It would take time. And now for our next part of the solution, our part B. So we have to solve for acceleration A. So we could solve this with kinematics, but I've decided to not solve it with kinematics, since it could be quite confusing for many if we use kinematics, and it would be a lot easier if we use Coulomb's law, even though it looks a bit more complicated. So let's go. So here is our Newton's second law formula. F is equal to ma, and by simplifying this to isolate our acceleration, we obtain F over m is equal to a. And now we substitute on F the entire Coulomb's law formula. That's basically it. So again, this is our 9 times 10 raised to 9 Newton meter squared per Coulomb squared. That is our proportionality constant. Again, these two are the charges of the two protons. These two. And this is distance squared of the distance squared of the two protons initially, which is the 0.750 times 10 raised to negative 9 meters squared. And that's basically our entire Coulomb's law formula that's equivalent to our electric force. Again, in our problem, they only say that it's the only force in affecting the two protons. So yeah. So next, this is our mass. Note that it's this all over this. So yeah, 1.67 times 10 raised to negative 27 kilograms. And we have all of that now. We can plug that into our calculator, and we would be able to obtain our acceleration, 2.45 times 10 raised to 17 meter per second squared. And since it's acceleration, it's highly likely that we will be able to obtain it immediately after release. So that's it for our solution for 23.9. Again, since our final velocity, this is our final velocity rather, 1.36 times 10 raised to 4 meter per second, and this is our acceleration, 2.45 times 10 raised to 17 meter per second squared. So I hope I was able to help you guys with 23.9, and I'll see you in our next problem for chapter 23. Thank you. This is our second problem for chapter 23, and this is a problem with a basic application of the conservation of energy and the electric potential and electric potential energy relationship. So here's the problem. A small particle has charge negative 5.70 microcoulombs and mass 2.70 times 10 raised to negative 4 kilograms. It moves from point A, where the electric potential is VA is equal to positive 270 volts, to point B, where the electric potential is VB is equal to 830 volts. The electric force is the only force acting on the particle. The particle has speed 5.90 meters per second at point A. What is its speed at point B? Is it moving faster or slower at B than at A? Explain. So as I've said earlier, there's the application of the conservation of energy formula, which is simply Ki plus Ui, which is wherein Ki is the initial kinetic energy and Ui is the initial potential energy, as I've written over here. U is potential energy and K is kinetic energy. And same here, except now the F stands for final. And since the electric force is the only force acting on the particle, we can say that there is no non-conservative force acting on the particle. Next would be our electric potential and electric potential energy relationship, which is simply U is equal to VQ naught. Since our formula for U is simply Q naught over R. This is a charge and this is another charge. And of course, K is our 9 times 10 raised to 9 constant. And R is our radius. It could also be signified with D, which is distance. It simply indicates something about the distance between either center to the surface, which is radius, or simply the distance between two particles. So for this case, we should actually be using D, so let's change that. So over here, let's use D. And there, D. So these are the two main formulas we will be using for our problem over here, and I'll show you how in our solution later. First, let's identify our given first. So let's see, there's a charge of negative 5.70 microcoulombs. And we can say that is our Q naught. It's the charge of a particle, so negative 5.70 mu c, which is just microcoulombs. And next is this mass of the particle, which is 2.70 times 10 raised to negative 4 kilograms. Next would be this thing, this VA. It's already written in the proper notation for electric potential, which is in volts. And I believe they used VA because they wanted to only emphasize that it's the electric potential from point A. So here, point A and the electric potential is 270 volts, while for point B, the electric potential is VB, and that's 830 volts. It's already written in the same notation that I put in the given as well over here. And next would be this speed. And as stated at the problem, it's the speed at point A, 5.90 meters per second at point A. So that would mean that it's a velocity at some point, but since it's directed from point A and it's going to point B, as stated over here, it's traveling from point A to point B. That means that's the initial velocity. So I put it as our VA over here. I just put it as VA, though we could just write VI if you wanted to use kinematics. But let's use VA instead. 5.90 meters per second see VA point A. And our unknown, as stated in this part of the problem, is VB. It's simply the speed at point B. It's kind of like our final velocity for this problem. And we also need to explain if it's moving faster or slower at point B and why. So we've identified our given and we've also identified all of our unknowns. So let's head to our solutions now. Again, here's our explanation for VB being the final velocity. Since the point travels from point A to point B, we can say that VB is actually the final velocity. So here we can start with our conservation of energy formula, the Ki plus Ui is equal to Kf plus Uf. Then over here, we substitute for all of the U our electric potential and EPE relationship, which is this one over here. So notice how I use for the initial values. For the UI, I used VA. As I've said, it's our initial since it's moving from point A to point B. And I've used for this one VB since that is our final. And for this one, this is simply the equivalent of kinetic energy, which is 1/2 over mv, 1/2 times mv squared. So this is our initial, again, VA, velocity A, then this one is velocity B. And by transposing this VBQ to the other side, we can isolate VB over here, V squared B rather, along with 1/2 m multiplied to it. So we have to multiply both sides by 2, like this. Multiply that to 2 over there. So that's why we have it over here now. Then divide both sides by m over here. Then we have to square root everything since once we isolate our VB, it's still V squared B actually. And look at this. It's still V squared B. So we have to square root whatever we get after isolating everything, after removing this 1/2 m by multiplying it by 2, the left hand side and the right hand side, and by dividing everything by m. So in short, this is the final equation that we'll be getting. This is the simplified equation to get VB. And now we have to substitute everything to get our VB. Here it's quite long, so again, this is 2, 1/2, this is our mass as given earlier. This is our initial velocity, VA, squared, plus this is positive 270 volts, the electric potential at point A. And this is the charge of the particle, negative 5.70 times 10 raised to negative 6 coulombs. Again, that's from the micro coulomb, so I just converted it to coulombs. Same with the 830 volts times the negative 5.70 microcoulombs over here. And of course, like the one in the initial formula, we divide this entire thing by the mass, 2.70 times 10 raised to negative 4 kilograms. And by plugging all of that into our calculator properly, remember, be careful with this 2 over here. It should be outside everything. That's why I put parenthesis, so that this entire thing would simply be multiplied to 2. So by plugging this into our calculator, we would be able to obtain our VB, our velocity B, and we would be able to get 7.65 meter per second. That is our velocity at point B. And since the magnitude is higher, that's our explanation for why the velocity at point B is greater than that of point A. So that wraps up our solution for question number 23.13, and I'll see you in our last question. So, hi guys, this is our last problem for chapter 23, and this is problem number 23.39. And here's the problem. The electric field at the surface of a charged solid copper sphere with radius 0.210 meters is 3,900 Newton per coulomb, directed toward the center of the sphere. What is the potential at the center of the sphere if we take the potential to be zero infinitely far from the sphere? So this problem has the basic application of electric field and electric potential. It's quite simple really. And here's the formula for our electric field. E is equal to kq over r squared, k being the proportionality constant 9 times 10 raised to 9, q being the charge, and r being the radius. Same goes for V is equal to kq over r, V being our electric potential. The only difference between our electric field E and our electric potential V formula is the r at the denominator. Anyway, it's quite a simple problem. Let's solve for our unknown. So, over here we have a radius 0.210 meters. So let's put that over here as r. Then we have this electric field 3,900 Newton per coulomb. So let's put that over here. And since it's directed inwards, or as the problem puts it, directed towards the center of the sphere, we say that it is negative. It's directed inwards. So that's about it for our given and our unknown as stated here. What is the potential at the center? All we need is this, our electric potential. So our solution is simply, first we need to solve for Q. Okay, so we're gonna use our electric field formula to solve for our Q, since we're going to need it for our electric potential formula, kq over r. So by simply multiplying r squared to the left hand side and dividing it by k, we're able to isolate q on the right hand side as shown over here. And since we have all of the given on this side, we can substitute it like this. See, this is our electric field E, negative 3,900 Newton per coulomb. And this is our radius squared, 0.210 meters squared. And this is our proportionality constant K. That's equal to our Q charge. And we would be able to get negative 1.91 times 10 raised to negative 8 coulombs. So that's our Q now, and we can now use that to solve for V with the formula V is equal to KQ over R. So let's just directly substitute everything like this. Again, this is our proportionality constant, 9 times 10 raised to 9. And this is our result from earlier. Let's put the negative sign from there. This is our Q from the earlier part of our solution over here. And this is our radius from the given over here. And we can plug that into our calculator in order to obtain an answer of negative 819 volts. That's our final answer basically for this problem. It's quite simple. Again, the final answer is negative 819 volts. And in order to solve for it with our given, all we need to do is solve for Q by using the electric field formula E is equal to KQ over R squared. Then substitute that Q to the formula for V, electric potential V, the KQ over R, and that's it. You'll be able to obtain your electric potential V. So that's all for chapter 23, and Thank you!